Hi, and welcome to AP Chemistry Review. It's me, Dr. V, and it's my favorite time of year. We're going through free response questions from past AP Chemistry exams. In this webcast, we're looking at free response question number 2 from the 2021 exam. Question number 2 on any AP Chemistry exam is always one of the long free response questions. And the long free response questions, as you may already know, are scored out of 10 points, and they have multiple parts. You'll want to make sure you have your calculator and your periodic table and your AP Chemistry equation sheet handy before we go through the rest of the webcast. And the reason for that is I really want you to listen to me present the question stem and then pause the video and try to work through it on your own and try to come up with your own answer before you listen to my explanation and see my solution. That's really what's going to help you develop as a chemistry student the most. And that also makes it possible for you to score your work as you go. And the advantage to doing that, of course, is that you can get a sense of whether you're showing enough work and giving a detailed enough explanation to earn the point and to enhance your answers if that's what you need to do. Let's jump right into the problem. Question number 2. Answer the following questions about the element silicon and some of its compounds. Part A. The mass spectrum of a pure sample of silicon is shown below. So a mass spectrum has mass on the x-axis here in AMU, and the y-axis is relative abundance, relative numbers of each isotope. And the question for part A, part 1, is how many protons and how many neutrons are in the nucleus of an atom of the most abundant isotope of silicon? Now, the most abundant isotope is the one that's got the tallest peak, and that's the one with a mass of 28 AMU. But that's not the answer that we need. We know from the periodic table that all atoms of silicon have 14 protons. It's got an atomic number of 14. That's literally what it's telling us. Therefore, since we know the isotope has a mass of 28, that's the number of protons plus the number of neutrons. So we can work backwards to calculate the number of neutrons. 28 minus 14 would give us 14 neutrons. And so our final answer is 14 protons, 14 neutrons. You don't actually have to explain how you arrived at that. I wanted you to see where I was coming from, but that's the gist of your answer. 14 protons, 14 neutrons. And if you wrote that down, that's your point. Now we're asked to write the ground state electron configuration of silicon. We know that a neutral ground state atom of silicon is going to have 14 electrons because it's got 14 protons. And a neutral atom, of course, has equal numbers of protons and electrons. And it doesn't say what format we need to use for the electron configuration, but we do need to make sure all 14 electrons are represented and that we follow all the rules of electron configurations. I like to do arrows and boxes. That's usually my first approach for writing an electron configuration unless I'm told otherwise. So notice I'm going to start with 1s and then go to 2s. After 2s comes 2p. There are 3 p orbitals in that 2p sublevel, followed by 3s and then my 3p sublevel, which again has 3 orbitals in it. I'm going to fill up 1s, 2s, 2p, and 3s completely. That leaves me with 2 electrons in my 3p sublevel, and based on Hund's rule, I'm going to have 1 electron in each spin aligned. Now, there's nothing in the question that said I had to write arrows and boxes, so I could have written spectroscopic notation. Again, I need to make sure all 14 electrons are there. It would have been perfectly acceptable to write 1s2, 2s2, 2p6, 3s2, 3p2, which is very reasonable. Silicon's in the 3rd period of the periodic table, so it should end with 3 for the principal energy level, and I'm in the p block, and I'm 2 columns into the p block. Alternatively, I could have written noble gas configuration, so use the symbol neon to represent the first 10 electrons, and then representing the valence electrons, 3s2, 3p2. Any one of these would be appropriate and would get you full credit. Go with the one that you can write the fastest. 2 compounds that contain silicon are SiO2 and SiH4. Part B goes on to say, at 161 Kelvin, SiH4 boils, goes into the gas phase, but SiO2 remains as a solid. Using principles of interparticle forces, explain the difference in the boiling points. And the key here is really about what's holding them together. So if we think about SiH4, it's going to be a molecular solid. What do I mean by that? I've got discrete molecules of SiH4. I drew 2 copies of my SiH4 Lewis structure side by side. And these molecules are going to be nonpolar. And because they're nonpolar, the only way they can interact with each other is through London forces. Induced dipole-induced dipole attractions help to hold these together, but these aren't very strong attractions. SiO2, however, is a covalent network. all of these silicon atoms are surrounded by oxygen atoms, and there are covalent bonds between them. And then those are surrounded by silicon atoms, which have covalent bonds. So they're all covalently bonded to all the atoms around them. And that makes for a very rigid and hard structure and a giant macromolecule. So the real focus of your answer needs to be that the London forces that keep the SiH4 molecules next to each other are really weak, much weaker than the covalent bonds holding SiO2 together in that giant macromolecule. It's relatively easy to take the SiH4 molecules, put some energy in, and overcome those attractions and have them go into the gas phase. If we want to break covalent bonds in the SiO2 macromolecules, we're going to need a lot higher temperature to make that happen, to get it to boil. And that's really the gist of your answer. And this is what you needed to talk about to get the point. In order to answer this part of the question successfully, you really need to know some examples of covalent networks. For AP Chem students, there are two common examples you should know: SiO2 and diamond. I've got a visual here of SiO2. Hopefully you're all familiar with diamonds. They're very hard materials. They have very high boiling points. They're insoluble in water because of these networks of covalent bonds connecting all the atoms to all the surrounding atoms. If you know these two examples, you should be good to go. At high temperatures, SiH4 decomposes to form solid silicon and hydrogen gas, and we're asked to write a balanced equation for the reaction. SiH4 is our sole reactant. It's going to undergo decomposition. So I'm going to write SiH4, and it is a gas. And then I'm going to make solid silicon and hydrogen gas. Those are my products. Before I write that, I want to remind you that hydrogen gas is a diatomic molecule, H2, and we have to make sure it's represented that way. So we're going to make Si plus H2, and in order to balance the equation, I need a coefficient of 2 in front of the H2. Of course, we're always going to have a balanced equation. And this is what you needed to write to earn the 1 point for this part of the problem. I do want to point out that states of matter were not required, so you didn't have to include that unless you felt like it, and that's fine. A table of absolute entropies of some substances is given below. Oh, hydrogen, silicon, SiH4, we've seen these before. Explain why the absolute molar entropy of silicon is less than that of the hydrogen, which we see in the table. I mean, we're given that information, so how do we explain it? Silicon is a solid, and if we think about solids, the particles are arranged in a very definite structure. There's a lattice here to the arrangement of the atoms, and they're not free to move around, right? They can really just vibrate in place. It's very ordered, and the atoms have a fixed position. So it's a low entropy state. It's a low disorder state. Hydrogen gas, of course, is a gas, and the particles are very far away from each other, and they're moving around, which I don't really show well in the static model, but there's a lot of space between those molecules. The molecules are spread out and they're changing locations, and there's a lot of different ways to arrange the molecules, and of course it's always changing. So when we talk about entropy, we really want to talk about how many ways are there to arrange the particles. We have a lot more possibilities with a gas than with a solid. A formal way of saying this, there are more available microstates for hydrogen gas than for solid silicon. Another way you could phrase this is to say there's a greater dispersal of matter for hydrogen compared to the solid silicon. Either one of these would be fine. The College Board's really not happy with the use of the word disorder when discussing entropy, and you're much safer talking about available microstates. Are there fewer or more available microstates, or talking about dispersal of matter with these entropy-based arguments, just as a word of advice. But that's the core of what you needed to say to earn the point here. Part E goes on and says, calculate the value in joules per mole per Kelvin of the entropy change at standard conditions for the reaction. Now, we, of course, already had the reaction. To find the entropy change for the reaction, entropy is a state function, so we can do the sum of the entropies of the products, find the sum of the entropies of the reactants, and that'll give us the overall entropy change. We wrote the equation in part C. SiH4 makes Si plus 2H2. The states of matter in the reaction match the states of matter given in the table. And so we can sum up the products, which are Si and H2, and subtract the entropy of the reactant, since there's only one of them. So I have to remember that there are two H2 molecules, so I do the solid silicon plus 2 times 131, and then I subtract the 205 for the SiH4, and I end up with an entropy change for the reaction of positive 75 joules per mole per Kelvin. And that is what you needed to do to get the point here. You didn't need to show the work to support how you got your answer. Part F goes on to say, the reaction is thermodynamically favorable at all temperatures. Explain why the reaction occurs only at high temperatures. The short version of the answer is, it must have a very high activation energy. Only at high temperatures do enough reactant molecules have enough energy to meet the activation energy minimum. And the College Board really likes questions like this, where it's thermodynamically favorable, but it only occurs at a certain temperature range. If it's only occurring at a high temperature range, it's always going to come back to that activation energy minimum. This is worth exploring a little bit more. So if we think about a Maxwell-Boltzmann distribution, where the x-axis is kinetic energy and the y-axis is relative number of particles, we can actually have the activation energy for the reaction indicated here, and that's what that dashed arrow is showing. And the area shaded in blue is the proportion of molecules that are over that energy minimum, that have enough energy to react. If this is a really large number, it's really a fairly small fraction of the molecules. At higher temperatures, here's a sketch of what that Maxwell-Boltzmann distribution curve might look at. What we see is at the higher temperature, a much larger fraction of the molecules are above that activation energy minimum. Right? I have a lot more up in this region of the graph, and therefore the reaction can occur more rapidly. That's the core of what you needed to say to earn the point here. And just as a quick thermo refresher, when we say something is thermodynamically favorable, in this case, delta G is a negative value at all temperatures in this problem. And that would mean that delta H would be a negative value and delta S would be a positive value. You didn't have to include that in this answer. I'm just trying to help you review. And now we're on to part G. A partial photoelectron spectrum of pure silicon is shown below. On the spectrum, draw the missing peak that corresponds to the electrons in the 3p sublevel. So we've got the binding energy on the x-axis, and that is a measure of the Coulombic attraction between an electron and the nucleus. And the y-axis is the relative number of electrons. We know from earlier in the problem that silicon has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p2. So we need to represent those last two electrons in the 3p sublevel. In terms of reading the PES spectrum, the peak with the highest binding energy is the sublevel that's closest to the nucleus, which of course would be the 1s sublevel. And then we can go from left to right here and label the other peaks. So we have 1s and then 2s. The tallest peak here is 2p. The next peak is 3s. And we don't have the 3p sublevel, but we know that that should be to the right of the 3s sublevel on this graph. And then we need to think about the amplitude for the peak. The peak height, of course, is proportional to the number of electrons in that sublevel. And that's why the 2p peak is 3 times as tall as the others. So we know the 1s orbital with those 2 electrons is the amplitude that we need, because we have 2 electrons in our 3p sublevel. And so we need to draw a peak that is to the right of the 3s peak, but the same amplitude as that 3s peak. And so we should be drawing something like this. That's our 3p sublevel. And that's what you needed to draw to get the 1 point. You didn't have to explain how you got there, but that's what you needed to do. Part H says, using principles of atomic structure, explain why the first ionization energy of germanium is lower than that of silicon. And I'm going to give you a hint here. Anytime they say use principles of atomic structure to explain a periodic trend, make sure you talk about either the Coulombic attraction of the electrons to the nucleus or the number of occupied energy levels. That's always what you need to focus on with these kinds of questions. So for silicon, if we look at the electron configuration, the outermost electrons are in the 3p sublevel. So here's a shell model visual for that. For germanium, the valence electrons are in the 4p sublevel. And the 4p sublevel is farther from the nucleus than the 3p sublevel. And therefore, the outermost electrons in germanium are farther away from the nucleus than in silicon, and they experience a weaker Coulombic attraction to the nucleus than the outermost electrons in silicon, which were in the 3p sublevel. Coulombic attractions, more shells, farther distance from the nucleus, that's the gist of your answer. Therefore, it takes less energy to remove the outermost electrons from germanium than it takes to remove the outermost electrons from silicon. And that's what you needed to say for 1 point. You didn't have to have the drawings, but you really needed to talk about the additional occupied energy levels and Coulombic attractions here. I do also want to mention, though, that you need to keep your answers really brief. You are pressed for time in the AP exam. You don't have time to write the great American novel. Bullet points are great. Keep your answers short, sweet, get right to the point. I wrote a lot here because I'm trying to be very detailed, but this is not an exam setting. So make sure your answers are very terse. Don't write unnecessary information because it won't help you. And now we're on to part I of the problem. It's a long problem. A single photon with a wavelength of 4.00 times 10 to the minus 7th meters is absorbed by the silicon sample. Calculate the energy of the photon in joules. I've got a wavelength, I want energy. The easiest way to do this is to use the equation E equals hc over lambda. I can derive this from E equals h nu and C equals lambda nu and put them all together. I like to just use this form of the equation. H is Planck's constant, C is the speed of light. They're both constants and they're on your formula sheet. And I know the wavelength. Lambda was 4.00 times 10 to the minus 7th meters. Notice it's already in meters. So I don't even have to convert from one unit to another. I can at this point substitute and evaluate. I know H, I know C, I know lambda. I can put them in. I like to include all my units. I'm left with joules as my unit and I get an energy of 4.97 times 10 to the minus 19th joules. And this is what I needed to have for 1 point. I needed to show the work and have a correct answer to earn the point here. So how did you do? This was a fairly long problem focusing on atomic structure and periodic trends. A fairly manageable problem nonetheless. The average score on this question in 2021 was 4.66 out of 10. So students did quite well. As AP Chemistry questions go, the average score here is pretty high. So if you got 5 points out of the 10, you're doing just fine. If you got 7 or 8 points, you're doing very well. This was a question where students who are well prepared could get all 10 points, and that's really what you're aiming for here. Subscribe to my channel, and if you found this helpful, like the video and leave the comment. And keep studying chemistry every day. That's the road to success.